Hi, dear MECH 533 students. This video record is to highlight the tricky details to pay attention in dealing with thermal stress analysis using the tools of Inventor NASTRAN. But in Inventor NASTRAN, first, only considering the heat transfer phenomena need to determine the temperature distribution. And then, the results of this analysis, such an analysis, is to be transferred to the duplicated version of the analysis. In doing this, there are some details, tricky details to pay attention. Although I tried to underline them during the class session, considering that, in time, at least such details may be forgotten, I decided to make a review on such things and also record. Whenever someone forgets a detail or missed a detail, then watching the video record can call. Okay. Yes, the object is not a matter it is in this shape or another shape. The important thing is the procedure. If the problem is the one when the thermal energy is transferring from one side to the outside to the other side across the body. Meanwhile, the object gonna be under the action of a certain loading, then yes, the stress distribution is important, more important, especially if the temperature is higher at certain threshold value, then over there the material may lose its strength. The atomic bonding forces drastically decreases, and the loads cannot be balanced by the atomic bonding forces. So, if there is a heat transfer across the body, then we should be careful and determine the stress distribution considering the temperature, changing values of temperature. Okay, now in this example, it is a rectangular prismatic object. It might be more complex in shape, not a matter, but the things to do, to determine the thermal stresses, gonna be the same, not a matter the shape is simple or difficult. But in this problem, in this example, say that this end of the prism has been rigidly connected, fixedly connected to a hot body, and from that hot body, thermal energy is conducted. Around this rectangular prism, say that we have atmospheric air, so convection heat transfer, natural convection heat transfer take this place, and the energy will be transferred thanks to the convection type heat transfer, through the via the air molecules. Although the thermal energy is transferred by the air molecules, we are going to see that the temperature of the body, even at its free end, won't be equal to the free stream temperature of the fluid. Okay, now first, although our objective is to check whether under the action of the applied forces the stress will be in plastic elastic region, plastic region, or there will be a failure. Determine the stress analysis, performing the stress analysis, and determine the stress maximum stress using the von Mises yield criteria. But it is a must in Inventor NASTRAN, using Inventor NASTRAN. First, the thermal part, only the thermal part of the problem is to be studied, is to be analyzed. Okay, well, clicked on environment tab, and then the software to use, well, the embedded software to the structure of inventories, Autodesk Inventor NASTRAN. Clicked on this tab, and then yes. First, have a look at the material of the object. Clicked on this button. Okay, and although after creating the model of the object, input the material and convert it to solid model, but if the software is NASTRAN, then the material assignment is to be repeated. Clicked on select material tab, and select the library, and in this example the material is stainless steel, and the characteristic fixed by American Iron and Steel Institute. It is code is 304. Right click the mouse, and then make a click on this, and then say OK. If the analysis is thermal analysis, well, here in this dialog box, it is a mess. Make a click into this little box to say that consider the thermal capacitance, specific heat, and thermal conductivity. Okay? It is important. Failure theory, von Mises. Yes, von Mises. And then OK, clicked on OK button. Well, bring the cursor to idealization option at the browser, and then see solid 1 is the corresponding idealization setting. It keeps the idealization setting. Have a look at, right click the mouse and say edit, and then check whether the material here has been selected. Yes. And also say that the element is not shell but solid element. This is not a shell. In this example, object is not a shell. OK. Click on OK button. Mesh model, mesh generation, generate mesh. Well, OK. Clicked on generate mesh button. Such a discretization is OK for me in this example, in this making analysis for this case. If the mesh size is to be decreased, precision is to be, accuracy is to be further increased, then well, it can be changed. You know how it is. Mesh setting and then change. Okay. Right click and then edit. Yeah, element size 17 millimeters. It can be decreased, or sweeping this furtherly toward fine can decrease the size of the elements, via which increase the number of elements. Smaller element size means higher accuracy, but oppositely greater time, process time. You know this. Okay. Yes. Now increase the precision, finer mesh. Okay, mesh setting is okay. And then, well, bring the cursor onto the analysis option. It is just the top icon at the browser. After the icon, it corresponds to the object, of course. And whenever NASTRAN is selected in environments along the environments ribbon, then NASTRAN automatically selects a linear static analysis option. But here it is not static analysis, but thermal analysis in this example. So bring the cursor onto analysis icon, right click the mouse and select edit option. Okay, then well, in the dialog box it appears. Well, here of course the unit, change the unit, or if necessary, of course, change not cat model. I'm going to select SI unit system. Okay, I want to see the values: length in meter, mass in kilogram, force newtons, temperature Kelvin, and so on. That's okay. And then here, of course, well, the important thing is to do is that drop this list and say, teach the software that it is not a constant temperature analysis, stress analysis, but it's a heat transfer problem, heat transfer phenomena. From this list, select linear steady state heat transfer option. Okay. And then clicked on OK tab. Yes. And then yeah, the boundary conditions. Thereafter, deal with the boundary conditions. Bring the cursor onto the load tab, and then, well, drop the list, and then from the list select heat flux option. Into this box, write the magnitude of the heat flux. Its unit is watts per meter squared. Well, in this problem, across this surface, well, from the hot body, there is a heat flux, heat input. Well, its magnitude in this example is 100 watts. But here need to write the value not in watts, but watts per meter squared. What is the area of the surface? Well, without stopping the analysis, interrupting the analysis, clicking on finish button, without clicking on finish button, well, click on inspection tab, and then take the instrument into hand, digital instrument, and then indicate the surface. Its area is 16,000 millimeters squared. Okay. 16,000. I'm going to convert it to millimeters, say meters squared. 16,000 millimeters squared. Well, 16,000 millimeter squared. Well, if I divide this number by 100, I know the unit will be centimeters squared. If I divide the result of that division by 100, I know that the unit will be decimeters squared, and divided furtherly by 100, then I know that it is going to be in meters squared. Okay. Now the area of the surface is 0.016 meters squared. Okay. If I'm divide the thermal energy, it is transferred from the hot body across the surface to this prismatic part by the area, I can determine the flux. Okay. Well, it is 100 divided by 0.016. This means 6,250 is the flux. 600 and, sorry, I forgot the number. 6,250. 6,250 watts per meter squared. Okay, is the heat flux. Already selected the surface and then clicked on OK button. Well, this means forgot to select the surface. Well, indicate the surface. First indicate the surface. I forgot to make a click on the surface, so we'll say for a while cancel. Okay, and then indicate the surface, and then clicked on boundary condition inputting button, and here select from the list heat flux option. Into that box write 6,250 watts per meter squared is the heat flux in this problem, and then say OK. Then yes, this green bar is the indication that there is a heat flux across the surface. One more time, click on first, for being safe to side, indicate the surface. This surface, now I'm keeping the control key of the keyboard as pressed, toggled on, to indicate more than one entities, that surface and the other surface. These are the vertically directed surfaces. I selected those vertical surfaces and then clicked on boundary condition inputting button. From the type list, select convection heat transfer option, and then say in this example the outer temperature, the outside temperature, surrounding temperature, free stream temperature is 20 degrees Celsius, let's say, plus 273 is the temperature value in Kelvin. Okay, it makes 293 Kelvin. That is the ambient temperature. Okay, convection heat transfer for the vertically oriented surfaces, heat transfer coefficient is 20 watts per meter squared Kelvin. Okay. Well, these are the boundary conditions for this case, sub-case 1. It is important. There may be more than one cases. This is the case. Actually, at present, it is the first case, only case, sub-case 1. Okay. This is important. Sub-case 1. In this pane, it is written that the problem or these parameters are for such a case. And then click on OK button. Yes. This tiny green lines is the indication that for the surface there is a convection heat transfer coefficient for this surface. It has been defined, it has been fixed. Okay, well, for the top side surface, indicate the surface first and then click on the boundary condition inputting button. Subcase is the same case, subcase 1, check it. Okay, not force, but here the boundary condition is just for convection heat transfer, the convection coefficient. Ambient temperature, free stream temperature is the same, 293 kelvins. Okay, and the convection coefficient is 10 watts per meter squared Kelvin, and that's it. Okay. And bottom side surface, make a click on the bottom side surface. This surface actually is an obstacle for the say the air molecules. Heat transfer can be achieved if the air molecules can move almost in the horizontal direction till reach to the outside of the solid body completely. So, because of such a prevention, the coefficient is smaller. Select from the list convection option. Ambient temperature is the same around the body. Okay. The convection coefficient is, let's say, 5 watts per meter squared Kelvin at the bottom side. Okay, then I think that's okay. We are ready to run the problem, to solve the problem. Click on Run button and then find the temperature distribution. Yes. Temperature distribution. Here, the maximum temperature at the root of this extended surface, 377 Kelvin, minimum 311 Kelvin. Okay, that is the temperature distribution across the body. And this is, if the problem type is only like this thermal analysis, then that's okay, finish the analysis. But if this is making such a thing is just the preceding stage for the rest, then at the rest following stage say that it is gonna be the time to define the mechanical boundary conditions, force, moment, body forces, etc. Then say the first step of the analysis has been completed. Okay, finish the first analysis. Click on the save button. And then, continue on the rest. In this example, this object is not free to atmosphere without any loading, but it is under the action of some external forces. Okay. Now, to be able to have the properties of the material at not uniform temperature, but while the heat transfer is realized across this body from its root to the outside of the object, we have different temperature values at different points within the body. Okay, need to consider the temperature distribution in determining the atomic bonding forces per unit of area. If the temperature is not uniform, then such a non-uniformity will directly affect the stress values. Okay, at higher temperature, then the strength of the material will be smaller. While the temperature increasing, the strength of the material decreases. Okay, well, unfortunately in NASTRAN, we haven't got a push button to define or to teach the software that it is thermal stress analysis type problem. Well, since it is so, first we should perform the heat transfer analysis and then be able to transfer the temperature distribution, okay, to the other mode in which the bonding forces, effect of external internal loading, body forces can be studied well while the temperature is not uniform within the body. Okay, to be able to transfer the result of the thermal analysis, okay, to the mechanical analysis domain, well, the first thing to do is that after finishing the thermal analysis, bring the cursor to the browser, make a click on analysis icon, right click the mouse, and from the list it will drop select duplicate option. Duplicate. Yes. Now the thermal analysis option is inactive, while the duplicated one is active. Okay. Here, bring the cursor onto this icon and then right click the mouse. Say edit. In this dialog box, now in this duplicated one, the copy you see, we have the boundary conditions, load 1, load 2, load 3, load 4. These are, the first one is just heat flux type boundary condition, the other is convection coefficients. Say. But in this copy, we have the result of the thermal analysis. But here in this dialog box, after saying right click and edit, this dialog box appears. In this dialog box, need to drop the list, and from the list, select static analysis option. Linear, non-linear, non-linear. If the limits will exceed, when von Mises stress gonna be higher than the yield stress, then select non-linear option. Okay, I don't know whether the stress will be higher than the von Mises stress will be greater than the yield limit stress. If yes, and then if you don't know that whether it is gonna be the material object will be in elastic region or exit region and reach the plastic region, then in first trial you may select linear static. Okay, or if there is a doubt that probably, if you say that probably while the yield limit will exit it, then at the beginning select non-linear static option. Okay. Say that first check whether von Mises stress will be greater than the yield limit. Select linear static. But if you have already checked that the material will reach to plastic region, then do not waste time. Directly select nonlinear static option. Okay. And then, yes, when you finish the running, do you want to see the results? Force, strain, stress. Well, wonder the stress value. So when stress output set, select stress. But you know, after having the scale in the vicinity of the model, the object, model of the object, then drop a list and select not stress but force, not force but strain, not strain but factor of safety. Okay, why there is no factor of safety option? If I change the type from non-linear static to linear static, have a look at, well, as the output said, strain energy, strain force, and well, can find the factor of safety option. But if it is non-linear, then factor of safety is commonly calculated dividing the tensile, dividing the yield limit, dividing the stress value by the yield limit. How many times the stress is, yield limit divided by the stress. It is to say that the stress value is whether 3 times smaller than the yield limit, 2 times smaller, n times smaller. Okay. But in plastic region, well, the important thing is that whether the stress is less than the tensile limit. Okay. Ultimate stress, less than the ultimate limit. Okay, nonlinear static, and units already selected. The unit is SI, that is okay for this analysis as well. And the others, I think, okay, clicked on OK button. But here, still one more time, have a look at the browser. I have the thermal boundary conditions in the list of loads for boundary conditions, let's say. But when I say OK after selecting static analysis option, then software, this is a trick, noticing me that if I say OK, then this thermal analysis data, thermal boundary conditions will be removed. At this stage, it is unavoidable to say yes, yeah, what can we do? Okay, then remove these boundary conditions. But of course, if we remove the boundary conditions, this means we lost the result of the thermal analysis, although it is a must to have in the static, in the mechanical analysis. But here at that stage, we need to say OK. After saying OK, at the browser, you see there is no thermal boundary condition. But don't worry about it. And after that stage, can invoke the result of the previous analysis, thermal analysis. See how. Well, clicked on the boundary condition inputting button, okay, and then drop this list, and from the list, say from output, select from output option. It is the option to click to be able to transfer the result of a certain calculation to the environment of the software for the active analysis. Select from output. This is a trick. Another trick is that from output. After clicking on this from output option, then well, show the results file, data file in which Inventor keeps the results of the analysis is where. Clicked on the button on which we have triple dots. It is to bring the search dialog box, and in the search dialog box, show the address of the data file in which we have the result of the previously studied thermal analysis. I know where it is. It is within this folder. It has been created by the software automatically, inherently, in cat finite element, and this is the file, okay, in which we have the result of the thermal analysis. Well, need to transfer this data. Now here at present at the browser, we have no boundary condition, thermal type boundary condition, but after indicated it with a click, and then say in this dialog box open, and then clicked on OK tab, then you'll see at the browser we have an item. It keeps the temperature distribution. Okay, we know within this body now, thanks to the transfer data, we know the temperature distribution. NASTRAN knows the temperature distribution. Yes, now, okay. Achieve to gather the data from the previous analysis. And then the rest is just the mechanical boundary conditions. Well, I know that this end of the prism is in well, fixed contact with a hot body. So, well, there is a mechanical constraint here, fixed connection, indicate the surface, and then say OK. Over the surface, top surface of the body, there is a distributed load. Say from this script, I know that y-axis is in the up direction, vertically oriented. Well, write the magnitude of the resultant of the force distribution into this box. Well, in this example, the load has only the y component. Okay. If it has the components in the x, in the z directions, then of course fill in the other blanks. Here the magnitude of the force is 1000 Newton. It is not tension loading but compression loading. Well, since the y-axis is in the up direction, I know that the force is in the opposite sense. This number is to be written as negative. Okay. Of course, here I selected force. It is a force in this example, and then say OK. Forgot to select the surface. No entities have been selected. Well, indicate the surface, and then say OK. Yes. Well, yeah, we'll have another loading. Say that there is one more load acting onto the surface. Indicate the surface first. Otherwise, it may be forgotten to click. And then say that, the force is tension type force, and it is in the negative direction of the x-axis. So say minus, magnitude is 500 newtons. That's it. It is a force. And then say OK. Mesh size is OK for this analysis. If not, then you can change it. Material, have a look at material for this analysis. Yeah, yes. Solid 1 copy. Well, this is our body option. The idealization is for this one. Solid 1 copy is the idealization option. The material, have a look at the material is the same. Autodesk material library, stainless steel. AISI 304. Select this and then say OK. Now we need to consider thermal analysis. Okay, select this one. But say this is important to select in performing the thermal analysis, not for performing the mechanical analysis. No need to select this box. Okay. One says is the failure theory, and then clicked on OK button. Material is OK, boundary conditions are OK, and idealization, copy, right click and say edit for being safe, decide the material, check whether it is the correct material, and it is to be solid element, not shell. These are all okay. And then the rest run the problem. Our mesh model, there's an exclamation mark. This means I need to generate the mesh again. Okay, then ready to click on run button. Since I selected nonlinear stress analysis, then Inventor will gradually, step by step, increase the magnitude of the loads. Okay, not 1,000 Newton, but 100 Newton, and then second iteration it will use 200 Newtons, and then 500 Newtons, and then so on. Step by step, increasing the magnitude of the loading, will check whether at which loading yielding will occur. So it is an iteration. It takes greater time, of course. Yes, iteration 1. Now, Inventor NASTRAN increase the magnitude of the loads. Of course, the final value of the load is 1,000 over the top surface, 500 Newtons, while acting to the free end of the body. It is still in the first iteration. Since I selected finer mesh size, you see the solving time is greater. Okay, dear students. In this video record, I hope I managed to underline the tricky details, tricky stages to pay attention. I don't want to make this video record furtherly too long. Obvious that, this problem will continue till it is being solved. It is still in the first trial, first iteration, and then second iteration, third iteration, so on and so forth. Okay, and then finally we find the solution of the problem. Okay, dear students, stress value only says stress. Clicked on this listing arrow and select megapascal option. I want to see the results in megapascal. Yes, it is a number I remember for this material. The yield limit is in the order of 300 megapascal, but here the maximum stress is 4,600 megapascal. No doubt, in the vicinity of the root, the material reached to plastic region under the available higher temperature. Okay, plastically deformed, obvious. Okay, dear students, I'm going to finish this video record. I hope you understood or gonna understand watching this video record. That say, in using the tools of Inventor NASTRAN for solving thermal stress analysis type problems, it takes greater time and you should know the tricky details. Thermal analysis first, and then duplicating region, and then, well, there is a trick to transfer the results of the thermal analysis to mechanical domain, uh, and then, well, the boundary conditions, etc. I think, well, in my video record, these are all clearly explained. Okay, dear students, well, I'm stopping the record. Stay healthy, and then I wish you a happy Eid Ramadan.